I made a few slides for this teaching demo because I thought it's easier to show some graphs and some equations. And the slides is largely adapted from EECS447 and EECS445 discussion notes. So before actually we talked about the attention mechanisms, I think when I learned about NLP and machine learning, especially when we are dealing with natural languages, I think the biggest problem that I always think about is how do we use numerical values to represent the words in the sentence. Because our models, like the neural network, can only compute numbers but not words. So people came up with the idea to use some vector representations to represent the words, in a sense that different words would have different representations and similar words would have similar vector representation. In other words, larger cosine similarity. And in this famous glove embedding, with this example sentence, the artist who paint, which has 4 tokens in total, we embed each word independently without capturing the contextual meaning. As a human, if we look at this sentence, the artist who paint, especially on the word paint, if we only look at this word, a lot of people will think that this is a noun that describes a drawing on the wall or on the canvas. But if we look at the meaning of the word under the context of the sentence, we will see that it is actually a verb that describes the action of the artist. So this ambiguity of the word is resolved by looking at the context of the sentence. But if we use this traditional embedding, it is clearly that this embedding doesn't capture these nuances because each word is embedded independently. So if we use such embedding to do some tasks such as translation or some predictions, we might receive some errors. So that brings up to the self-attention mechanism, which allow each token in this input sequence to attend to every other token in the sequence. So which means that given the input, given a specific word in the input token, we have the embedding, and we can refine this embedding by incorporating more information that relates to the relationships of this token with all tokens in the sequence. This helps the model to disambiguate meanings and relations dynamically based on the context, on the sentence context. A more concrete examples, going back to our example at the beginning. For the sentence who has 4 tokens, the artist who paint, we now have 4 embeddings, x1, x2, x3, and x4, corresponding to each token. And for each x, we calculate the corresponding query key and the value by this equation with this weighted matrices. These are learnable parameters that we learn in the training process. So now we have query key and value for each token in this input sequence. So let's say we want to know a good representation of the word artist under our input. What we want to do is that we take the query of the artist, which is Q2, because artist is the second word in our input sequence. We take the Q2 and we take all the key values inside our sequence, K1, K2, K3, and K4, and we take the dot product correspondingly to get 4 scores. And for the scores, we do sort of like a normalization by dividing the square root of the dimension, and then we do a softmax to add some non-linearity. After that, we got 4 alphas. We represent the weights of how this word artist evaluate its relations with all the tokens in the input sequence. And the final step we want to do is that we multiply the values of each token with its corresponding weights. And then we got H2, which is attention-based contextual embedding for the word artist. And from this example, we can see that the new calculated H2 is a better representation than the original embedding X2 because it incorporates those more information that describes the relationships of the word artist with all the other tokens in the input sequence.